All right. So I will continue some of the chapter 4. I think I'm mostly working, at least to start with, these are problems from section 4.5. And I think I've already worked some of these, but just kind of attack some from each section, try to work them pretty quickly, go from there. Number 10. Here we're solving 10 to the 2x squared minus 3 equals 10 to the 9 minus x squared. So since we have, base 10 on both sides, we could just take the log of the equation, for example. And if we do that, what happens? Just calculate the common log of both sides, like log of this equals to log of that. That gives me 2x squared minus 3 equal to 9 minus x squared. Of course, you can get what I just wrote in blue simply by applying the one-to-one property of the logarithm, right? Now, and so then what are we facing here? We got 3x squared equal to 12, right? So x squared equals to 4, which tells me that x is plus or minus 2, right? So that's number 10. Forge ahead here, let me do a different one. I'll do number 28. Um, 2 times 5 plus 3 to the x plus 1 equal to 100. So every one of these, the instruction is to solve the equation, okay? So what I need to do here is to isolate the exponential, right? That's pretty much the goal. Once I've isolated the exponential, then I can take a logarithm of it and solve it. So to isolate this exponential 3 to the x plus 1, I can divide by 2, right? Dividing by 2 gives me 5 plus 3 to the x plus 1 equals to 50, right? Because 100 over 2 is 50. And then subtract 5 from both sides, right? 3 to the x plus 1 equals to 45. And then there are various ways you could proceed here. You could be clever and solve it without a calculator, maybe. But I think what I'm going to do is just kind of use the heavy-handed approach I usually use myself when I'm working on things, and I don't really care too much about proving to people that I'm clever or anything. I just take the natural log of equations like this. You could take log base 3. That would also be fine, right? So I'll let you guys choose the adventure. What do you want to do, log base 3 or natural log? All right. So natural log of 3 to the x plus 1 equals to the natural log of 45. Now, by properties of the logarithm, I can pull x plus 1 out, right? X plus 1 times the natural log of 3 equals to the natural log of 45. Then, remember, natural log of 3 is just a number. So we can divide both sides by log 3, and we get x plus 1 equals to the natural log of 45 divided by the natural log of 3. Now, if you're a proponent of using the log base 3 way of solving this, then you would have actually got to what I just got to directly. Let me just mention this in passing. Change of base formula says that this is equal to log base 3 of 45. So like if you look at it, x plus 1 equal to log base 3 of 45, this is what we would have got from here if we just took log base 3 of both sides. So like using log base 3 to solve a problem like this is smart, but it's also not helpful if you don't have a calculator that can do log base 3, you know? I mean, so it's a mixed result here. So let's ignore what I've written in red for the moment, all right? Let's finish the black work here. And so what I get is x is equal to the quotient, the fraction natural log 45 divided by the natural log of 3 minus 1. And there you go. That's the answer. Let's see here. I see heaven has arrived. And Jason, right? Okay, so let's try to work on number 38. Number 38, we're asked to solve 10 over 1 plus e to the minus x equals to 2. All right? So I'm going to give you guys a minute to work on that, and I'll be right back, okay? So everyone try to solve that. Just give me a second here. I'll be right back. All right, so what we got? Any answers?
Yeah.
Multiply 10 on both sides? I don't know what you mean. Do you mean?
Or 1/10.
Oh, like, so divide by 10?
Yeah.
So then that we have 1 over 1 plus e to the minus x equals to 2 over 10, which is 1 over 5. Okay. And then what?
I thought you could just multiply 10 on both sides, and then you could have, you would have 1 plus e to the x, negative x power equals 20, and you minus 1 on both sides, you have 19, and that's natural log of 19.
Oh, Well, I think there's something right about what you're saying. Let me just, I mean,
So,
how about this? 10 is equal to 2 times 1 plus e to the minus x, right? So we can multiply both sides by the denominator
oh, okay.
to clear it out.
I understand. Okay. So then you divide 2 on both sides.
Mm-hmm. So we get, yeah, 5.
Then you divide, okay, yeah. I understand. Thanks.
But your general goal was to isolate the exponential, and that's right on point. That's what we want to do.
And then you have 4,
Mm-hmm.
and then you take the natural log of 4.
Yeah, natural log of 4 is natural log of e to the minus. What is the natural log of e to the minus x equal to? What's that? Minus x, right. And so x is equal to minus the natural log of 4. Yep. All right. So next up, let's work one of these exponential equations of quadratic type. The one I'm about to do is definitely different than the ones we have done so far. I mean, all three of these examples that we've done so far, kind of the same method to solve it, right? Like we basically isolate the exponential and then take logarithm, and that solves it for us. Or in the first one, we could use the one-to-one property since we had the same base on both sides. But problems 39 through 44 in section 4.5, these are a little bit different in the way that they're solved. I'll do number 43. Here we have 2 to the x minus 10 times 2 to the minus x plus 3. Actually, this one's even a little bit weirder than the other ones. And this, I'll have to do another one after I do this one. We'll do this one, then I'll follow it up with number 41, actually, which is e to the 4x plus 4 e to the 2x minus 21. In fact, maybe we should do the number 41 first. Might even be more natural to do that. Let's do 41 first. That is equal to 0. So what you want to do here is you want to let y equal to e to the 2x. And the reason we want to do that is because if we do that, then we can take this kind of equation and look at it as a quadratic in y. What is e to the 4x equal to? Well, what's y squared equal to? Right? So by properties of the exponential, if we square an exponential, it multiplies the argument in the exponential by 2. So we get y squared is e to the 4x. So in view of this substitution, right, we can re-image this problem, if you will, as y squared plus 4y minus 21 equal to 0. And well that's a quadratic, right? Which we know we can solve by completing the square, but we should try to be lazier first, right? We should just try to solve it by factoring if we can. Can we solve this one by factoring? 7 and 3, which one is positive, which one is negative? Y plus 7, y minus 3. So that says what? Y equals to minus 7, or y is equal to 3, right? Now, are we trying to solve for y? No, we're trying to solve for x, right? So now we have to undo that substitution we made and like work back to x. So what are the or the equations we face. We face e to the 2x equal to minus 7, or e to the 2x equal to 3. Now, we don't have to go any further. The left equation, we just look at it, we go, no solution, right? Can an exponential be negative? No, right? Like the range of the exponential function is 0 to infinity, and minus 7 is not in there. It's like this is no solutions. If you tried to take the natural log of that, you'd end up with like natural log of minus 7, which is not defined, right? You believe me? Okay. I mean, you can disagree if you want. And how about the other one, though? We take the natural log of that. What does that give us? Yeah, natural log of e, you say negative 6. Natural log of e to the 2x equals natural log of 3. What's the natural log of e to the 2x, though? It's just 2x again, right? It's 2x. So we get, 2x equals log 3. So what's the answer? X equal what? 1/2 log 3, right? Of course, you could also write that as the natural log of the square root of 3 if you wanted, right? Because we can pull a half in and make it into a square root if you want. But anyway, log 3 over 2 is a fine answer by me, right? So you guys, look at this problem number 43. You can also make that into quadratic. What are you going to make your substitution there? Or do we need to do something else first? Let's see. Yeah, I think we need to do something first, because like if I try to make 2 to the xy, then y squared would be like 2 to the 2x, right? That doesn't help. If I try to make 2 to the minus xy, well, that makes y squared y to the minus 2x, right? So that's not going to help. But this one, what you want to do first is multiply the whole equation by 2 to the x. If you multiply this by 2 to the x, we get 2 to the x squared minus 10, because remember, 2 to the minus x times 2 to the x is what? 2 to the 0, right? Which is 1. In other words, these cancel. So let me rewrite that. We've got 2 to the x quantity squared plus 3 times 2 to the x minus 10 equal to 0. By multiplying the equation by 2 to the x. Now it's a problem that's like problem number 41 with that little step. But in my book, because that little step is required before you can do this, this problem is twice as hard as problem 43. Because that's, you know, I don't know, like, I could see a lot of students not seeing that needs to be done, right? I mean, it's kind of, maybe if it occurs to you, then great. If not, well, I guess you better hope your instructor showed you that problem. I think some instructor showed me that step at some point. But anyway, what should I make the substitution? Yeah, let y equal to 2x. I think that'll do it. Oh, it's the same as the other one, isn't it? That's funny. So let y equal to 2 to the x, then this is y squared plus 3y minus 10 Can you guys factor that? 5 and 2, which one's positive, which one's negative? Positive 5, negative 2. So that tells me what? Y equals to minus 5, or y equals to 2, which is to say that 2 to the x equals to minus 5, or 2 to the x is equal to 2. But there's no solution to the negative one, right? No solve. And this one here, well, notice if we put 2 to the x is equal to 2 to the 1, right? Then we can use the one-to-one property. What's the answer? The answer is just x equal to 1 by one-to-one property of the exponential function. So, of course, you could also take the natural log of both sides and then divide by the natural log of 2. You'd also get back x equals to 1. I mean, so there you go. A couple of those. Few more problems to show you in here. Let's look at, so now we're transitioning over to equations involving logarithms, all right? Well, actually there's some, oh fine, I missed one. Curses. I'll do number 48 up here. Number 48 is x squared e to the x plus x e to the x minus e to the x equals to 0. So notice that there's like a common e to the x, right? So we could factor out e to the x. Let's do that. Oh, man. So we've got x squared plus x minus 1 times e to the x equals to 0. But what can you tell me about e to the x is what? It's non-zero, right? So we can divide by e to the x. Like, cancel out e to the x, and we're just left with the quadratic x squared plus x minus 1 equal to 0. So this is just divide by e to the x, which is, by the way, non-zero, right? How do you solve x squared plus x minus 1 equal to 0? Yeah, complete the square, I think. I don't think I can factor this one. So this is x plus 1/2 squared, right? And then minus 1/4 minus 1 equal to 0. So that gives me x plus 1/2 squared equals to 5/4, right? Because 1 is 4/4, and 4 plus 1 is 5, and bring it to the other side gives me positive. Then I take the square root of both sides, and I get x plus 1/2 is equal to plus or minus the square root of 5/4. So therefore, x is equal to minus 1 plus or minus root 5/2. And thankfully here, we didn't make a substitution, right? So like I'm not worried about either one of those solutions being extraneous, because at no point did I make an algebra step which has strings attached, right? E to the x is not equal to 0. That's a categorical truth. It's always true. So, yep, there you go. I think those numbers are famous. But anyway. All right, let's look at like number 50. It sure is nice when factoring works out, isn't it? But every so often, completing the square is what we got to do. So you gotta watch out for that. Number 50, log base 5 of x plus log base 5 of x plus 1 equals to log base 5 of 20. So I think, Taylor, you're telling me you were working on like properties of logarithms, right? 4.4, right? So now we get to use those properties of logarithms to simplify this equation, right? So what? Yeah, log base 5, x times x plus 1. So we're using that, the sum of logs is the log of the product property of log, right? Now that's equal to log base 5 of 20. And so now you've got log base 5 of something equals log base 5 of something else. At this point, we can appeal to the one-to-one property of the logarithm and conclude that the arguments are equal. So by one-to-one property, x times x plus 1 equals to 20. So the solutions are 4 and 5. Wait a minute, no. Well, 4 is the solution. Anyway, we shouldn't guess, right? How do we solve a quadratic equation? What? How about x squared plus x minus 20 equal to 0, right? Can you factor that? X plus what times x minus what? Plus 5 minus 4 equal to 0. All right. So this tells me that x is equal to minus 5 or x is equal to 4, right? What's the trouble with minus 5? It's negative, right? But what's the, I mean, well, we allow negative numbers, right? Right, that's the thing, is if we go back to the original problem, we notice that log of minus 5 and also the log of, base 5 of minus 5 plus 1, both undefined, right? In other words, x equals to minus 5 is outside the domain of the original equation. Right, so x equal to minus 5 is an extraneous solution, so we can say, this one doesn't count. Right? X equal to 4, on the other hand, you can check it, right? Log base 5 of 4 plus log base 5 of, 5 is equal to log base 5 of 20. I mean, you can plug 4 back into here, into the original equation, and it works. So there you go. That is the answer here. 4. Let's try out another one of these. Like number 52. Natural log of x minus a half plus the natural log of 2 equals 2 times the natural log of x. Again, we're supposed to try to solve this thing, all right? So I think my first move is going to be the right-hand side I can change to the log of x squared. And then the left-hand side, the log of the sum, the sum of logs is the log of the product, right? So like this is the natural log of x minus 1/2 times 2. And then we can take the exponential of both sides, or we could use the 1-to-1 property for the log. But however you want to slice it, this gives us that 2x minus 1 is equal to x squared. Why do I have 2x minus 1? Because if we multiply 2 times x minus 1/2, we get 2x. And 1/2 times 2 is 1, but there's a minus, so I get a minus 1. You guys follow me? And looks like we're back to solving a quadratic equation yet again, right? So how do we do that? Well, x squared minus 2x plus 1 equal to, hey, that's equal to x minus 1 squared, isn't it? So this one's actually a repeated root case for the quadratic, and the solution is 1, right? Now, to be fair, to be safe, I should really go back and make sure that that solution works. The reason for that is whenever you take the log, we use this property with combining logs. If you happen to have the case that this was negative and that was negative, it could work out that the product is positive, and so you're like getting that positive solution, but when you track back, it would be negative, negative, which would be trouble. I don't think that's going to happen here because that's 2, so it's always positive, right? So like, I think this step actually makes sense without qualification. But just to be safe, we should check our answer, right? Again, logically, I think it's needless. If I plug 1 back in, I get 1 minus 1/2, which is 1/2, right? What's the log of 1/2? That's the log of 2 to the minus 1, right? That's minus the natural log of 2. So when you plug in 1 back into this equation, the first term becomes minus the natural log of 2. So you get minus the log of 2 plus the log of 2. So the left-hand side of this equation works out to 0. What happens when we plug in 1 over here? Well, we get the natural log of 1 squared, right? Or 2 times the natural log of 1. Either way you slice it, you've got 0. 0 equals 0, good, it checks. So, yep. All right, now problems 55 through 68, they've got kind of a different flavor to them. Let's see how those go. Ah, rats. Number 58. I'm trying to work mostly even problems. That way, if you want to work the odd problems, you've got something to try, you know? Because the answers to the odd problems are in the back of the book. But of course, honestly, like, you could check any of your answers to any of the problems just using like Wolfram Alpha or something if you wanted. Now, when we just write log, what does it mean? That's log base what? What's our convention? Base 10, right? So how do we solve this? We do 10 to the log base 10 of x minus 4 equals 10 to the third power. Of course, 10 to the third power is 1,000. And 10 to the log base 10 of x minus 4 is just x minus 4. So we get x minus 4 is equal to 1,000. Therefore, the solution is 1,004. That's how you do these. Well, this one anyway. Let me look at another one. Number 60, we have log base 3 of 2 minus x equals to 3. So you guys tell me what to do on this one since I did the first. I did the first one, you do the second one. How about that? You want to tell me? You what? You just erase it, and that makes the problem go away. I like the way you think. What's that? If you don't see it, it's not there. That's right. Oh man, so many political jokes to make right now. Anyway, 3 to the log base 3 of 2 minus x. You're thinking that? 3 to the 3. Which is kind of funny looking, but there it is. And of course, 3 to the log base 3, those are inverse functions, so they cancel out, right? And this gives us 2 minus x equals 3 to the 3, which is what? 27. So therefore, x is equal to minus 25. Well, I guess we could try number 62. Here we're solving log base 2 of x squared minus x minus 2 equals to 2. So what do? Raise it to what? Raise it to 2. Yeah, so 2 to the log base 2 of blah is equal to 2 to the 2, right? Which is to say that x squared minus x minus 2 is equal to 4, which means x squared minus x minus 6 is equal to 0, which is to say x times blah times x times, well, what's the? Minus 3 plus 2. And so our solutions, apparently, are x equals to 3 and x equals to minus 2. And in this one, they both work because the original problem was not broken up into 2 logs, right? Like it was, these both solve this equation. So can you factor this original one? I mean, this is what? This is x minus 2 times x plus 1, right? So in principle, you could look at a corresponding equation, right? Like, if you wanted to, like, this is the answer to the problem, right? I'm just adding commentary at this point. But in principle, you could look at the corresponding problem, like log of x minus 2 plus log base 2 of x plus 1 equal to 2, you know? And if you looked at that, then if you combine these logarithms, you'd get back to the starting point of this problem, which was that log base 2 of, you know, this just equals to 2, right? But this problem does not have both of these as the solution, right? This problem has 3 as a solution, but minus 2 does not work as a solution because minus 2 makes both of these negative. So we've got to be careful. When we apply properties of logarithms, we're changing the equation, like the solution set. How do you judge whether or not you've made a genuine, in some sense, genuine change to an equation? Like, we say two equations are equivalent if they share the same solution set, right? So if the modification you made changes the solution set, then most commonly people say that those equations are not equivalent, right? But we do this all the time, right? We make operations, we change to an inequivalent equation, which we can solve, but then the thing is we have to go back and check the original problem. So whenever we're solving equations and we make certain steps, we've got to be aware, we've got to go back and check. You know what, even if we don't make those steps, it's just a good habit to go back and check your work anyway. But so yeah, that's pretty much it for problems, or section 4.5. And I don't really have much anything to say about the rest of the chapter. There's like one other kind of problem I want to talk about with you guys here. And then I'll change topics a little bit here, the time that we have left. What's that? Yeah, I can leave. Should we wait for the rest of the class to get here? Or you don't think, we obviously should not do that, you're saying? Yeah, they're probably 100 miles from here by now, right? I'm being optimistic. If they're on campus and they're missing, then that's like more offensive to me. Yeah. Since you're 780 bonus points.
How many of us did you 1, 2, 3, 4, 5, 6? 6 times 600. And that's plus 200.
So here's a problem. So this is basically number 83 through 86 are all kind of like this. So here, I'll do one that's not even one in the book, but suppose you're given that f of x equals, you know, e to the 2x minus 3, all right? Find the inverse function to f. That is, calculate the formula for f inverse of y. So how did we calculate the inverse? We did this before, right? But we didn't have logs and exponentials back then, right? All we had were like rational functions, division, addition, multiplication, right? Roots. But now what we can do is y is equal to e to the 2x minus 3. And now we solve for x. So how do you solve for x if y is equal to e to the 2x minus 3? What if I take the natural log of both sides? The natural log of y is the natural log of e to the 2x minus 3. What is the natural log of e to the 2x minus 3? How does that, how does what is on the board simplify? Natural log and e cancel, right? So what does that leave us? Okay, very good. Equals 2x minus 3. And then we do what? We add 3 to both sides. We get 3 plus the natural log of y is 2x. So x is equal to 1/2 times 3 plus the natural log of y. There you go. This right here is the what? This is the inverse function of y. So it's the same exact algorithm that we did earlier in the course. To find the inverse function, we set y equal to f of x and we solve for x. Whatever you get, that's the inverse function. If there is an invertible, if the function is invertible. And you know, exponentials are 1-to-1, and so e to the 2x minus 3 is, well, anyway, we found the inverse. There's a proof that it's invertible. You can try plugging this in. You can try composing this with that function, and you should get back what you started. Let's try it out. What happens if we calculate f of f inverse of y? What happens then? So we would say f of 1/2 3 log of 3 plus log y. How do you do that? So that's equal to the exponential of twice the input minus 3, right? See what happens there? The 2 and the half cancel, right? The 2 and the half cancel, and then you get a plus 3, you get a minus 3, they cancel. And so this simplifies down to the exponential of the natural log of y, which is what? Which is y again, right? That's what has to happen for the inverse function. The function of the inverse function should give you back whatever you put in. This should be what's called the identity function. And we could go through a similar calculation for f inverse of f of x. Maybe we should do that. Let's try it the other way. What happens f inverse of f of x? I'm just checking our answer, okay? So f inverse of f of x would be f inverse of what? E to the 2x minus 3. And what's my formula for f inverse? We do 1/2 of 3 plus the natural log of whatever the input was. In this case, the input is 2x minus 3, right? So what happens there? The natural log and the e cancel. We've got 1/2 of 3 plus 2x minus 3. The 3 and the minus 3 cancel. And then we get half times 2, otherwise known as 1. So again, we get x. So if both this and that composition check out back to give you just the input again, that proves, if you will, that the alleged inverse function is in fact the inverse function. So just checking my work, but I'm not saying you need to check your work necessarily on this kind of problem. I'm just saying you can. Like this might be a problem in your homework. Like part A, find the formula for the inverse. Part B, show that f composed with f inverse of y is equal to y again. And part C, show that f inverse of f of x is equal to x again, right? That might be a three-part find the inverse problem, like the mission I'm about to write. That seems like a pretty good problem. Let's do one more of these. Can we find the inverse given, f of x equals to log base 7 of, 3x plus 1, find inverse, right? So can we do it? Well, step number 1, we write y equal to the formula. Now what do? Solve for x. How are you going to solve that equation for x? How do we get rid of that log base 7? What do we do? Raise it to the 7 power, right? So 7 to the y is equal to 7 to the log base 7 of 3x plus 1, which of course simplifies to just 3x plus 1. And so we've got 3x is equal to 7 to the y minus 1, which gives us that x is equal to 1/3 of 7 to the y minus 1. Now we solve for x. Whatever's left over, that's the inverse function of y. So that's it. I mean, that's the formula right there. So that's pretty much it for this section. There's one other topic we're going to explore in the homework. So let me just give you a brief introduction to these new functions I want to share with you. So the exponential allows you to build. Well, first of all, there's a trick that you may or may not have ever seen before. Probably haven't seen. If x in the domain of f implies minus x is in the domain of f for all x in the domain of f, then so this sentence of weird math symbols that I wrote, all I'm saying in that sentence is you have a domain where if you've got a positive number, you've got its negative. If you've got a negative number, you got its positive. You've got always matching x's from both sides of the origin. So people will say that the domain is symmetric about the origin. Exponentials like this, right? Any function that has the domain that's all the real numbers is like this. All right? Anyway, if that's the case, then you can write the following identity. F of x is 1/2 of f of x plus f of minus x plus 1/2 of f of x minus f of minus x. You're like, what? Why would you do that? Well, what did I do? I mean, so this plus that is just f of x again, right? But then this and that cancel, so that's just adding 0. But the reason to do this that makes it interesting is you can check that this is even function. And this one over here, this is an odd function. So what this little identity shows you is that any function whose domain is symmetric about the origin can be decomposed into the sum of an even function and an odd function. Remember we talked about the graphs of even and odd functions earlier this semester, right? You know how they work. They're like symmetric about the origin, or they're symmetric across the y-axis, right? So these are pretty nice functions, right? Even and odd functions. The cool thing is, if you apply this identity to the exponential, something really neat happens. E to the x is equal to 1/2 e to the x plus e to the minus x plus 1/2 e to the x minus e to the minus x. So I'm just, that algebraic identity applied to the exponential. It breaks the exponential up into two pieces: the even part of the exponential and the odd part of the exponential. And the even part of the exponential, this is a definition, this is called cosh of x. And this guy over here is called sinh of x. In other words, this is known as the hyperbolic cosine. And over here is the hyperbolic sine. Right. So one thing you can, I mean, here's some basic facts about it. Cosh of 0 is what? 1/2 e to the 0 plus e to the minus 0. What's e to the 0? Is 1, right? So this is 1/2 of 1 plus 1, which is 2 over 2, which is 1. So the cosh of 0 is 1. What's sinh of 0? It's e to the 1/2 of 1 minus 1. So like sinh of 0 is 0. All right. But there are all kinds of interesting things we can say about the hyperbolic sine and hyperbolic cosine. So you're like, well, you may or may not. So have you guys had any experience before at all with sine and cosine in like high school? A little bit. So you remember sine of 0 is 0, maybe cosine of 0 is 1. Maybe, maybe not, but it's true. So these are just like sine and cosine in that regard. What do you remember about sine and cosine? It satisfies the Pythagorean identity, right? Like cosine squared theta plus sine squared theta is what? It's 1, right? That one, that's a pretty big deal. Like you've definitely seen that. Just, yeah, like on a circle, right? Indeed, so, hey, perfect. So on a circle, if you have the unit circle and you pick a point on the unit circle, you can call that cosine t, comma sine t, right? If the angle here is t, right? That's how the unit circle in trigonometry works, right? So sometimes sine and cosine are called circular functions because they parameterize the circle in that sense. Hyperbolic sine and hyperbolic cosine, if I was to, say, look at a hyperbola, let's see here, like this perhaps. So this would sort of be the unit hyperbola. This has the equation